What's up guys, Scarce here. Today I'll be explaining the limit of a function. Now, the obvious question is, what is the limit of a function? Well, the formal definition states that if f of x becomes close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is L. Now I know that was a lot to take in, so let me give an example. For this problem, we are trying to find the limit of f of x as x approaches 2. And we know that the limit of f of x as x approaches c from the right must equal the limit of f of x as x approaches c from the left. So let's just apply that rule to this problem. We see that the limit of f of x as x approaches 2 from the right equals 2, as well as the limit of f of x as x approaches 2 from the left. So therefore, the limit of f of x as x approaches 2 is 2. Now, it's also very important to note that c does not have to equal x, for that is not what a limit is. A limit can be a whole. It doesn't have to be a defined point on a graph. Now, for a harder example, here we have the limit of f of x as x approaches -4, 2, and 4. We're going to try to find all three of those limits with this f of x graph here. So we're just going to apply the rule here. We're going to start with -4. As x approaches -4 from the left, we see that it is 6. And as x approaches -4 from the right, we see that it is 3. Therefore, the limit as x approaches -4 does not exist for f of x. Moving on to number 2, we see we are trying to find the limit of f of x as x approaches 2. So let's see it from the right, it approaches 3. And from the left, it also approaches 3. Therefore, the limit of f of x as x approaches 2 is 3. That is a very simple problem, very similar to the last example. For this final one, this one really stumps people because they see this defined point and immediately assume that that is the limit, even though this is also the whole is there, which is also part of the graph. So we're just going to use the rule here like all the rest of them, and we're trying to find the limit of f of x as x approaches 4 from the left, which appears to be 5, as well from the right, which appears to be 5. So the limit of f of x as x approaches 4 is 5, even though the defined point at x equals 4 appears to be 9. So that's a great example of how the limit does not have to be the defined point on the graph. Now, there won't always be a function or a graph to find the limit of a function. In most cases, there will just be an equation, such as these examples right here. Let's start with number 1, where we are trying to find the limit of f of x as x approaches 3, where f of x equals x squared minus 2x minus 3. I don't know why it says plus. Minus 3. So what you always want to do first with these problems is just go ahead and plug in 3 into the equation, or whatever x is approaching into the equation, and see what if you get a defined point. Let's see if we do it here. We get, plug it all in, 3 squared is 9, minus 6, minus 3 would be 0. Therefore, the limit of f of x as x approaches 3 equals 0. For number 2, getting a little bit more trickier, we see the limit of we are trying to find the limit of f of x as x approaches 3, where f of x equals x squared minus 2x minus 3, except this is all over x minus 3 this time. So we see here, if we try to plug in 3 into this equation, we end up getting a 0 in the denominator, and that is disgusting. But what we can do is in most cases, you will be able to simplify the top and bottom to get rid of whatever is causing a 0 in the denominator. So if we see here, we can FOIL this out. We end up getting x plus 1 times x minus 3 all over x minus 3. So now we can see that we can actually cancel out the x minus 3 at the top and bottom. We end up with x plus 1. When you plug in 3 into that, you get the limit of f of x as x approaches 3 as 4. Now for a third example where we don't have a graph, we have the limit of h of x as x approaches 4, where h of x equals the square root of x minus 2 over x minus 4. Once again, let's plug in 4 to see if we can get the value. We can't because we end up with a 0 in the denominator. Therefore, we have to simplify this and try to get rid of this x minus 4 in the denominator. Well, this is not a quadratic, so what can we do? Well, we can multiply the top and bottom by the conjugate. What this does, it gets rid of the x minus 4 in the denominator, hopefully, so we end up with a better value for the limit. So what we can do is multiply the top and bottom by the conjugate, which is square root of x plus 2 to the top and bottom. What that gives us, simplified, is x minus 4, when you multiply that, over x minus 4 times the square root of x plus 2. And that's what those equal each other. What we see, we can cancel out the x minus 4, that is an x. We end up with 1 over the square root of x plus 2. That is much nicer to plug 4 into. When we plug in 4 to this equation, we end up getting 1 over 4. So the limit of h of x as x approaches 4 is 1/4. Now for our final problem, this is actually an absolute value equation. And for these are a little bit more complicated than the past ones we've been doing. So we see here, we are trying to find the limit of f of x as x approaches 5 from the right. Not just 5, but 5 from the right. So that adds a little bit more into what we are trying to find. So we see f of x equals the absolute value of x minus 5 over x minus 5. And we cannot just plug in 5 into this. We end up getting a 0 over 0, and that is bad. So we can actually take, and this cannot be canceled because this is an absolute value. But what this does equal, the absolute value of x minus 5 can be turned into a piecewise function, where it would be we're trying to find x when it's less than 5 and x when it is greater than or equal to 5. And we see that x will be less than 5 if it is a negative number, so we'll just do negative x minus 5 to make that positive, and we'll do x minus 5 in the bottom when it is greater than x, when x is greater than 5. So now that we have these two, this piecewise function here, we can actually plug both of these into the numerator of the equation. So we'll have two equations, negative x minus 5 over x minus 5, as well as x minus 5 over x minus 5 down here, so you can see that. So now what we end up getting is we cancel these out. This will be negative 1. We cancel this out, we get 1. We're trying to find 5 from the right. We can see here that the limit of f of x as x approaches 5 does not exist, because from the right and left, the values are different. We're trying to find as x approaches 5 from the right, so we look from the right when x is greater than or equal to 5. We see that it is this equation, so it is 1. We now know that the limit of f of x as x approaches 5 from the right is 1. That's about it. Thanks for watching. Hope this helped. Peace.